first announcement is homework number 2 is due right now. So if you haven't submit your homework number 2, please do so ASAP to Dropbox folder on Visuals. Second announcement, homework number 2 solution will be posted tonight. Around right at 10 p.m. So you guys can go to Pitchboard and to download tonight after 10 p.m. You'll be there. If you have any problem to access the solution, please let me know. I think it should be fine because so far I think the Pitchboard is going well, unless there is any misfunction again. But anyway, if you encounter any question, just let me know. So I think that will be that to 2 announcements. And next week is the spring break, so we don't have any classes next week. So you should take the opportunity to prepare for your midterm 1, which will be Wednesday, April the 7th. So like we mentioned last time. So I think that's the overall announcement for today. So any questions so far?
Yeah, in this class, will we be only having like 1 midterm in the final, or will we be having 2 midterms in a final?
2 midterm.
Okay, thank you.
So read the syllabus is a 2 midterm. So like we said on the syllabus. And I said that before, midterm 2 will be scheduled on the last week of April for midterm 2. Last week of April will be midterm 2. Okay? Any questions, discussions? Okay, if not, we need to move on to section 4.5, we call local buckling. So we spent like a few weeks talking about the buckling and the column, and so far the buckling we talk about is global buckling. So today we need to talk about the local buckling. So in construction manual, the specification, when we talk about the compressive stresses, some or all of the cross-section elements, the steel section must be classified as being compact, non-compact, or slender, such that the appropriate strength equation can be applied. So in the specification, the cross-sections can be classified as compact, non-compact, or slender. So in manual B4, which is page 16.1-14, that is based on 13th edition, define the method which is used to classify a cross-sections. A cross-section consists of multiple place elements, like you guys already know. For example, like a W sections. You can think of the W section is composed of multiple plate elements combined together. Or you can say 3, top flange, bottom flange in the web, for example. And for those plate elements in the manual can be classified as stiffened or unstiffened elements. We'll talk about that in the next few slides. And for either stiffened or unstiffened can be classified as compact, non-compact, or slender. So the most restrictive case, for example, this will be the most restrictive, which is slender, the worst scenario. For example, if one of the elements in the section is compact, then the other element, for example, in the same cross-section is slender, then your total cross-section should be classified as slender instead of compact. So you got to pick the most restrictive case. For example, the most slender definition to define the classification of the sections. So the actual classification system is table in B 4.1, page 16.1-16. So this is based on 13th edition. That table describes various conditions how to compute the width over thickness ratio and the limits for lambda p and lambda r. So the lambda p is the separation between compact and non-compact, and lambda r is the separation point between non-compact and the slender. Alright? So all this value is tabulated. The equation is all tabulated in the manual. So in the next few slides, I'm going to cover first how do you define stiffened unstiffened elements in the cross sections. So once we define that, we need to know the limits for lambda p and lambda r, and then from there we can classify if the cross sections is compact, non-compact, or slender. So example, AIC specification classify the cross-sectional shape as compact, non-compact, or slender depending on the value of the width and thickness ratio of the elements. So for I or H shape, I is a W, the ratio of the projecting flange elements, which is unstiffened element, is BF divided by 2 TF. So BF is the width of the flange, TF is the thickness of the flange. And the ratio for the web element, which is stiffened element, is the height of the web divided by the thickness of the web. So the category of the shape is based on the worst unstiffened and stiffened element in this shape to define the cross sections. The worst width over thickness ratio to define the cross section is compact, non-compact, or slender. So for example, the web is compact, but the flange is non-compact. So the overall the shape will be classified as non-compact. We pick the worst scenario. Okay? So I think I should reorder like this. The worst scenario is slender, then is compact. Oh yeah, then is non-compact. Best is compact. So that would be the order. So, which is exactly what I said in here. So in this example, if your web is compact, your flange is non-compact. So your overall cross section should be classified as non-compact. You pick the worst scenario to classify your cross sections. So any questions or discussion about these slides? Any questions? All right, so I think these slides give you a lot of terminology and definition and symbol. So we will go over one by one. Now, for local buckling, the slenderness will be based on the width over thickness ratio of the slender plate element that make up the cross sections of the most steel member. So like I mentioned to you, for local buckling, it's classified by compact, non-compact, and slender. So the separation point will be lambda P and lambda R. But for column, the main thing we need to focus on is this separation point, slender or non-compact. All we care about is the member, the elements, the plate elements that make up the cross sections is slender or not. We really do not care. That is compact or non-compact. So for column, again, we only care about if the plate elements that make up the section is slender or not. Okay, so that's the main concern for compression member. But when we talk about the flexural member, for example, like a beam in chapter 5, then we need to consider all of the cases in here. When we talk about the flexural elements, which is beam, the bending, then the cross section need to be classified as compact, non-compact, and slender. But for compression member, like I said, we only care if the cross section is slender or not. All right? So all we really care is the lambda R limits. If your width over thickness ratio of the plate elements bigger than lambda R, then you say it's slender. If less than lambda R, then it's not slender. So that's for compression member. But for beam member, then you also need to focus on lambda P and lambda R to classify as a compact, non-compact, or slender for the elements as well as the cross sections. All right, any questions?
Yes, sir. Lambda P and lambda R, because of the pin member.
Can you speak louder, we?
Did you say that we're gonna focus for pin member between lambda P and lambda R?
We only focus on lambda R for compression member. But when we talk about chapter 5 for flexural beam, then you also need to consider lambda P and lambda R together. Okay? All right. So first of all, we need to define what is unstiffened and what is stiffened element. So let me see. Let's go to this. This figure 7 is in your textbook as well. This shows you the stiffened and unstiffened elements of various cross-section shape for compression member and the limits for lambda r, which is from table, construction manual table B4. So let's look at the W shape, for example. So for W shape, this is what we call unstiffened. Elements. And for the web, and then we call this stiffened element. So how to differentiate this is stiffened or unstiffened? So one way to think about is if this element is supported by 2N, then this is stiffened. So like this, projective flange, one end is free, another one is supported. So this is what we call unstiffened. So this is the basic definition you need to remember. So same thing, this is unstiffened, and this is also unstiffened because they have free end for each element. So both of this is unstiffened. Okay? Then let's look at this HSS sections. These elements, all of them are stiffened elements. All of them. You can think of this HSS made up of 4 elements, plate elements, 1, 2, 3, 4. Each element is supported by 2N. So for HSS, they are all stiffened elements. So likewise, for this HSS, they are all stiffened elements. Okay? So, with that being defined, let's go back to this W shape. The B over T, which is what I just mentioned to you, is equal to BF over 2. Times TF. This is the same thing because the distance from here to here is what we call BF. You need to divide by 2 to get B here. And TF is actually equal to T, the thickness of the flange. So the B over T ratio divided by a B over T ratio should be less or equal to 0.56 square root of E over Fy. So this is a lambda R for the flange, for unstiffened element. For the web, it's H over TW. it should be less or equal to 1.49 square root of E over Fy. So this is a lambda r for the stiffened elements for W sections. The edge, remember the edge. Be careful. The edge here is the distance from here to here, not from here to here. It's not the depth of the beam, no. The edge here is the distance between the top and bottom of the web elements. Just remember the definitions. And this is the lambda r for stiffened and unstiffened elements. As for HSS, each element B over T should be less or equal to 1.4. Likewise here, B over T should be less or equal to 1.4 square root of E over Fy. So that's what it means. So any questions or discussion about this slide?
So all these formula is to calculate lambda r.
Yeah, all the equation here is lambda r. That's the limits for slender elements. We'll go over one example about this so you have a better idea about how to apply this equation to classify for the cross section. We'll go over one example. Any questions?
No, sir.
All right, so let's continue where we left. The first 8 cases listed in the manual, table B 4.1, refer to unstiffened elements. The remainder cases are referred to stiffened elements. The table includes figures to illustrate the definition of different components. What the table does not include is a graphical representation of the stress distribution that apply to each case. The applicable stress state is included in the element descriptions. And note that the cases for unstiffened element do not include the effects of combined compression and bending. The equation conservatively assumes the uniform compression due to either flexural or compression elements. For the stiffened element cases, the combination of flexural and compression is considered separately from the cases of pure compression and the pure bending for W-shape or I-shape member. So this only affects the limit for lambda P, not for lambda R. So when we talk about the beam in chapter 5, or in the future, chapter 6 beam column, then you need to consider the limit for lambda P, and then you need to consider the compression and bending effect together, combined. But so far in chapter 4, we only consider pure compression. Okay? So the application of the case is discussed later in text, maybe chapter 6 in the future, when combined axial bending stresses happen in a member. That is chapter 6. That is way beyond this course. This we call combine bending and actual effects. But in this chapter, we only cover pure compression, no bending. Chapter 5 is pure bending, that is for pin. But in chapter 6, there's a case we will combine both bending and compression. That is chapter 6. That's the future. It's beyond the scope of this class. But anyway, this is only for your information. You don't need to pay too much attention or worry about this notes. Just for your information. What you really need to know is to where to find the table in the manual to find the limits for lambda r for stiffen and stiffen elements. So for I or W and the edge shape, the projecting flange, like I just mentioned to you, is considered as unstiffened elements, and it can be taken as BF divided by T divided by TF, which is BF over 2TF. And BF TF is the width and the thickness of the flange. The upper limits for lambda r slender elements is 0.56 square root of E over Fy, like I just mentioned to you in the previous slides. As for the web, for W and the edge shape will be stiffened elements, and the width is the distance between the roots of the flange. So it's classified as H over TW. So like I said, the H is the distance between the roots of the flange. TW is the thickness of the web. In the upper limits for slender elements, lambda r is 1.49 E. I think it should be this. So this should be cross out. Let's cross out this one. Any questions? So the square root should be outside, not on the denominator. Any questions?
No, sir.
Okay. So this is what we just talk about for W or H or I shape. So this is the graphical representation about local buckling. As you can see that there's a wrinkle happen. So this is what we call local buckling on the flange. Okay, so the slender, the elements slenderness, example, compact, non-compact, slender will be shown like this representation. Okay. And one more note will be for your information. If you go to part 1 of the manual, for example, I just throw out a sections. W 16 by 31, for example, you will see a C, a footnotes, C, right next to the notation W16 by 31 in the manual of Part 1. And if you read the footnote, they will tell you that these sections let me see, this section, let's say this, let me see. This section is slender for compression. So if you see a footnote C next to the designation of the shape, which means this shape is slender cross sections for compression. So if you guys have the manual with you, you can go ahead and check. Go to Part 1 of the manual. If you see a footnote C next to the shape designation, you will see the description. This section is slender for compression. Okay? So which means the manual already checked and classified the slenderness of the shape for you. Now, those are more graphical representation about the local buckling for stiffened and unstiffened elements. In reality. Okay? So like I said, the buckling stability alone is a one course in graduate school in the future. So if you guys are interested in this theory analysis, you can take the course Stability and the Buckling in graduate school in the future. Okay, but this is all what it comes from with all of this local buckling. Okay. So now, like I said, on stiffened and stiffened elements, where I highlight in here, and this for unstiffened, and this is for stiffened. So these are exactly the same like you see in your textbook. I just draw it with different color for you to differentiate. This is unstiffened, this is stiffened elements. So let's show one example. Example 4.2. I think example 4.2 we covered last week. W14 by 74 column. That's what we did the calculation for the global buckling strength last week, or I think it's on Monday. But now, example 4.3, let's examine and investigate if this column has local stability issue, local buckling. So what we can do is go to Part 1 of the manual, then you can read the flange width 10.1, the flange thickness is 0.785 inches. So for the width and thickness ratio for the unstiffened elements, which is this guy, in the W sections, is 6.43. The lambda limits for unstiffened elements is 0.56, square root of E over Fy, and which is 13.5. this number is bigger than 6.43, then this is okay. So meaning the unstiffened elements is non-slender. Likewise, let's check for the web. This one, stiffened elements. The ratio is H over TW and is equal to D minus 2 KDES. So what does it mean? What it means is the W sections, if you zoom in, the W sections actually has a kink or transition between the web and the flange. So you see these transitions. Okay, so this distance in part 1 of the manual we call KDES. So there are two on top and bottom. So your H is actually D minus 2 KDES. Is the design value of K. It's based on manufacturer. So in the manual, they give you the smallest value as a design value. So your H is D minus 2 KDS. Again, this number is coming from the manual as well on part 1. If you go to W14 by 74. So with that ratio, you got 25.4. The lambda R for the web is 35.9. It's bigger than 25.4. So this means your flange is non-slender and this means your web is non-slender. So because both of these are non-slender, so the conclusion, your cross sections of W14 by 74 is non-slender sections. So local buckling is not a problem. Any questions or discussions?
Professor?
Mm-hmm.
So the first two equations is going to be for the flange. The second two equation is going to be for the web. The first equation is going to be have to calculate lambda. The second equation is have to calculate lambda r, which is the upper limit for the flange.
Yes.
We compare it and we determine it's going to be non-slender.
Yes.
The last two equations, the first is for lambda and then
It's for the web.
For the web, yes.
Mm-hmm.
Thank you, sir. For the first equation for the web, what is D again, Professor?
Which one?
For the web, H over TW, and what is D?
This is the ratio of this guy. H over TW, the thickness of the web, is a width over thickness ratio.
Where did you get the 14.2?
This one, the D from manual.
Thank you, sir.
So if our answers were less than, would that be local buckling is a problem?
Less?
Yeah, because we got our numbers to be, or sorry, if it was like the other way around, would we get buckling?
Yes, it will be slender.
Okay, it wouldn't be like compact or anything. It'd just be slender.
It's not compact. When you bigger than lambda r, it's a slender. Then you have a local buckling issue.
Okay. Is there ever a case where it's equal to?
What's that?
Is there ever a case where it's equal to?
Equal?
Yeah.
It could be. If that's equal, it's also slender. So the equation here is less than equal. So if you are less than equal, they are fine. But you are bigger than slender.
Gotcha. Thank you.
Mm-hmm. Good questions. Any questions, discussions?
No, sir.
Okay. So again, all this value is coming from part 1 of the manual. You just plug into this to calculate h over tw. Likewise, bf over 2tf, all this value is coming from part 1 of the manual as well. So, if your lambda is bigger than lambda r, then to account for the local buckling effect, we need to use the reduction factor we call Q. So what you really need to do is similar to the global buckling equation you learned in class, you just need to consider Q. In these terms. To account for the local buckling effect. And here, I would like to make a note. Our lecture is based on 13 editions of the manual. So we use Q factor. If you are using 15 edition and beyond, they are not using the Q factor. They are using a C1 and C2 coefficient and factor to account for the buckling effect. So that one is quite complicated. So to be consistent in the class, let's use the Q factor that I cover in the class to account for the local buckling effect for your calculation. Okay, so remember the notes that I mentioned here. Use Q factor to account for the global buckling based on 13 editions. And if you use 15, I believe 14 editions still using the Q factor. I think it's 15 edition or so. They use C1 and C2 factor. That's way complicated than Q. Q factor already been very complicated. But this, instead of using Q factor, they are using C1 and C2 factor. And to calculate for that is quite complicated. So again, for exams, homeworks, let's use Q factor that I covered in class to account for local buckling effect. So any questions?
Since people who have the 15th edition have C1 and C2, so which one do we choose then, C1 or C2 to be our Q? Or are they both the same?
Use Q factor, not C1 and C2. Because we based on 13th edition for the class. Let's be consistent for that. Any other questions? So once again, for your exam homework, use Q factor to account for local Buckling effect. Any other questions?
No, sir.
Okay. So, the reduction factor Q is the product of two factors, which is QS and QA. So Q is equal to QS times QA. QS is for unstiffened elements, local buckling. QA is for stiffened elements, local buckling. If the shape has no slender unstiffened elements, then QS is 1. If the shape has no slender stiffened elements, QA is 1. So please take the notes. So once again, we are using the reduction factor Q in this class for homework and exams. So you got to be familiar with the reduction factor Q in this class. And this is more simple to learn as well. Many of the shapes commonly used as a column are not slender, so the reduction factor Q will not be needed. So this includes most but not all of the W shape. However, when you use the HSS, hollow structural shape, double angle, and T, some of them might have slender elements, and that's the time you need to account for the local buckling effect, which is the factor, reduction factor Q. But for W shape, for most of them are non-slender sections, so you don't need to account for local buckling. But when the problems have HSS, double angle, and T as the column elements, you need to check if there are slender element or not. If yes, you need to account for Q factor, reduction factor Q, to account for local buckling effect. In AISC manual specification E7.1 give you the procedure for calculation of QS for slender unstiffened elements, and E7.2 give you the procedure to calculate QA for slender stiffened elements. So this is based on 13 editions. So you might not have these two in your manual, but in the lecture, I will cover the procedure and equation for you. So don't worry about that. You have all of this that I will cover in the lecture. How to calculate QS and how to calculate QA for slender, unstiffened, and slender, stiffened elements. The procedure to calculate the QA is here. Please write it down. you need to compute effective area of the cross sections. And this requires the knowledge of stresses in the effective area. So the iteration will be required. However, the specification allows you a simplifying assumption. So iteration can be avoided. So I'll teach you maybe next week, after the spring break, the iteration versus non-iteration method. To calculate the effective area. And the QA, by definition, is equal to effective area divided by the total cross-sectional area. So AEFF is the effective area and A is the actual area. So that would be the QA. So once again, Q is equal to QS times QA. So if you are using 15 additions or so, write down the procedures for QA, like I mentioned here, and also the definition for QS. So in the next class, we'll go over the calculation example, how you do that. We will be using the HSS as our example to account for local buckling issue. Okay, so once again, this is based on 13 edition of your manual. Okay, all right, any questions? Any questions or discussions? So after we come back from the spring break, we'll talk about example 4.4, where we are going to talk about, for example, HSS, cross sections for a column. Then we need to consider both global buckling and to check if local buckling is applied. If we have local buckling issue, we need to calculate the Q factor. Let me give you a heads up. We need to calculate Q factor and to account for that local buckling and to calculate the strength for that. So this is an example I'm going to go over after we come back from the spring break. So this just give you a heads up. Like I said, for most of the W sections, those sections are not slender cross section. So usually you do not have to account for the local buckling reduction factor Q for that. Okay? All right, so I'll end today's class in here. So have a good spring break. So after we come back, we'll continue for the example for local buckling. So in the meantime, you guys are encouraged to work on the homework number 3 problems, maybe 1 and 2, or other problem you think you are capable of doing that. Do not wait until I finish the class. You need to get started to work on your homework number 3 because midterm 2 is coming soon, which is the last week of the April. Okay? All right, I will see you guys in 2 weeks.
Professor,
Professor.
Thank you.